So our first subject then is electrochemistry basics. Electrochemistry, electrochemistry basics. What we're looking at is if we take an electrode, let's make this one out of copper, and we put it into got a little bit of shine on my board. If we put it into a container and we magically apply a voltage, so we put it in a container full of water and we magically apply a voltage, because we need to worry about that in a moment, how we're going to do that. And we apply a positive voltage to make the copper dissolve, because there's no copper in the water. Then we would get, let's find a piece of board. So as we apply more voltage, there, whoops, this is for field, oh, you can't see that, it's E in volts. We will get more current, I. Let me fiddle with my camera a little bit. Okay, so let's rub that out and put E in volts here. E in volts, I in amps. Obviously it wouldn't be amps unless it was a very big electrode. As we increase the voltage, copper will dissolve, but we will reach a point when the copper dissolves and gets into solution very close to the electrode, and then is trying to redeposit, and it becomes harder to dissolve, so the current will curve off, and if we do it too hard we will start to deposit some kind of copper oxide, copper hydroxide on the surface, and it will interfere with our dissolution, limiting the current. In extreme cases it makes it go back down again, but let's do a simple case where we reach a maximum. So that would be a simple electrochemical process. If we now have copper in our solution, we could go the other way. So we could redeposit the copper, but again, if we deposit copper faster and faster, we will reach a place, which won't necessarily be the same current as before, we'll reach a place where we can't deposit copper any faster, because the copper ions in solution can only get there at a certain speed. If the concentration of copper next to the electrode is 0, then copper is diffusing to it as fast as it can, and it turns out that although the copper 2+ ions in solution are charged and our electrode is also charged, it's negative, they don't attract each other very much, which we will explain now. But first of all, I'm going to rub this off. If we have our copper, yeah, that is shitty, 2+ in solution, and we have our electrode, let's put the electrode here, and it is negative, so that's where the metal is. Then near to the electrode we will have some kind of ions. Let's have it in sodium chloride because it's simple. So let's have sodium plus close to our electrode, and next to our copper 2+, there will be a chloride minus, or maybe several. And that means at a relatively long distance, this copper 2+ ion cannot feel the charge on the electrode, no matter how high it is. So if we take a theoretical situation where we have a container with an electrode in it, we obviously can't have a single electrode. We'll have to explain how we're going to do that in the future. We can't have a single electrode and put a charge on it because the electrons have got to go somewhere. But if we put a negative charge on it somehow, which we will explain later, and we have two types of ions in solution, copper and lead, let's have 2+ lead as well, and that they can choose to go onto the electrode, then we will have the same situation as before, but we will have two processes that can happen. So our graph, which is on the negative side, will have two steps in it, like that, with the first process being one of these two ions, the one that's easier to reduce, and the second step being the other ion, which we don't know which is yet, but we could identify that later. So if we want to do this in reality, we would have to have another electrode. So let's have our real situation. We would have to have another electrode, and we would have to probably put some ions in the solution to make it conduct. Water does conduct, and the moment it gets some metal in it, it'll conduct better. But it's much easier and simpler to think about if we deliberately add some electrolyte. So let's have two electrodes. The simplest case is if they're both copper, but they then interact with each other in complicated ways. So if we have an electrode, we can put a power supply on it. Let's have an electronic power supply and not a battery. So let's have plus and minus. That will cause this electrode to be positively charged and this electrode to be negatively charged compared to each other. We don't know what charge they have compared to the solution, but we know that the same amount of charge, so if current flows in the solution, first of all it won't, if current flows in the solution, so we've got some ion, let's have copper in here, copper 2 plus, going to this electrode, oops, sorry, arrow's going the wrong way, collecting electrons from the electrode, and this way we've got a copper on the surface giving electrons to the electrode and coming off, so this is copper electrode, coming off as copper 2 plus. So we've got a simple copper cleaning process. If we do that, we can see that if we transfer charge across here, the same amount of charge will have to transfer down here, which means that the solution will be at a potential so that the current on this electrode is exactly the same as the current on this electrode. However, as I drew before, which I've rubbed out stupidly, a bit of a problem with board space here. Let's draw it like this. If I draw it right on that lens flare, sorry about that. Let me see if I can get it a bit higher. The advantage of this is I can draw smaller. Disadvantage is there's a lot of space where I can't draw on. A pen's going to die. Let's go to red. So if we have red and we have this process, that it's easier to dissolve the copper than it is to dissolve the copper than it is to deposit it. Then as we turn the voltage up, we will go up on both electrodes so that the current here is equal to the current here. Is that, yeah, that looks kind of right. But when we get to this little corner, when we turn down, this one will be stuck here, where this other one will disappear down to the next process, whatever happens. In this case we're depositing copper, so it's this one, and we will start to deposit hydrogen instead. We'll start to make hydrogen instead, which will be another process that happens out here. So if we need this much current, this voltage will have to go, this voltage which is on this electrode will have to go to here, and this one will only be here. This is our voltage axis, which in chemistry we write as E just to confuse you, but never mind. We will call this voltage because it's electromotive force in volts, And you can see that our solution will be such that this electrode is more negative than this one is positive, because it's a lot easier to get the copper to leave faster than it is to get copper that isn't there to deposit.